we will soon witness another giant leap in spaceflight. Starship Block 2 is on the horizon, bigger, stronger, and built to be fully reusable. A new design is taking shape, and it's not just an upgrade, it's a bold reimagination. Oh, what is this? A ship for humans? Bound for Mars? A sleeker stage separation? Ditching the hot staging adapter? A refueling system? In orbit? Yes, all of that. And more. This isn't just about rocket science. It's about solving one of the hardest problems in aerospace. How to send people and cargo across millions of kilometers. Not once, but again and again. Affordably, safely, and sustainably. And the pieces are moving fast. Production is accelerating. Designs are evolving. And the first flight of Block 2? Closer than most think. There's a storm of innovation behind the scenes. And yet, we've barely scratched the surface. Because the story of Starship Block 2 is just getting started. Indeed, there's a bunch to catch you up on. Full reusability, the core goal of Block 2. It's a good sign when SpaceX keeps testing, revising, and pushing the boundaries of Starship's design. And this time, the goal isn't just to launch, but to return and launch again. Starship Block 2 aims for something bold. Not only landing the booster, but also recovering the upper stage. Full reusability. The kind that can slash launch costs by factors of hundreds and unlock sustainable interplanetary missions. Should provide a great daytime view, watching both booster and ship return to Earth like a pair of futuristic space jets descending side by side. And behind that sleek spectacle is some very real engineering progress. The next section for Ship 38 has just been moved to the stacking bay, the lower body segment, now featuring redesigned mounts for the landing legs. These legs are critical for high-precision touchdowns. The ship's cylindrical frame is made from a next-gen stainless steel, lighter, yet strong enough to withstand dozens of flights and recoveries. Engineers are also experimenting with faster swap thermal protection tiles, designed to drastically cut the turnaround time between missions, a key factor if you're planning a Mars fleet. Some of the most vital components are now being fitted with sensors to track stress, fatigue, and material integrity. That data will feed directly into upcoming test flights, helping refine what might become humanity's most used spacecraft. Because unlike a one-off launch vehicle, Block 2 is being built to fly again and again with minimal refurbishment. The closer it gets to aircraft-like operations, the more transformative its impact will be. And soon, all of these upgrades will face their first big challenge. They're headed for an upgraded structural testing rig, the kind of machine that bends, twists, and crushes prototypes under load, until they either fail or prove they're ready to fly, ready to land, and ready to go again. But there's one more piece to the puzzle, without which Mars is still out of reach. How do you fuel a rocket in space? Orbital refueling, the key technology for reaching Mars. It's believed that the earliest attempts at orbital refueling may have suffered from fluid instability in microgravity. Engineers observed irregular flow rates during test simulations. Some speculated the issue stemmed from inconsistent tank pressure and the unpredictable behavior of cryogenic boil-off. In microgravity, fluids don't settle. They float, cling to surfaces, and behave in ways we don't typically encounter on Earth. To better understand the problem, several mock-up tests were conducted using small-scale tankers under zero-G conditions. These tests were likely designed to verify valve synchronization and the overall efficiency of cryogenic fuel transfer in orbit. The results? Partial success. While some sloshing patterns remained chaotic, the tests delivered critical data. Engineers used that feedback to redesign internal baffles, barriers inside the tanks that help manage fluid motion, and refined the flow regulators to handle unexpected pressure fluctuations. A combination of revised piping, improved pressure control, and active cooling seemed to mitigate the issue. That seemed reasonably plausible. What about the fueling interface on Starship Block 2? The system starts with two starships aligning in orbit, one serving as the tanker, the other as the receiver. Once docked through a custom-built mechanical interface, a closed-loop helium pressurization system kicks in, forcing chilled methane and liquid oxygen through thermally insulated lines from one ship to the other. At the heart of it is a central manifold, which manages flow rate, monitors tank conditions, and ensures pressure remains balanced throughout the transfer. Every component must work flawlessly, especially under prolonged zero-gravity exposure. The piping architecture includes expansion loops to handle temperature swings and vibration dampers to protect against structural fatigue. The tolerances are razor-thin. The consequences of failure, catastrophic. That's why every connection, valve, and sensor has to perform with precision. All these steps ensure a clean, steady transfer process, essential for fueling deep space missions. A super solid structure. Now, orbital refueling may be critical, but there's another piece of hardware that's quietly disappearing, and it could make Starship even more reusable. Dropping the hot staging adapter, a new design for flight efficiency and reusability. We also spotted this intriguing change at the base of the upper stage. The familiar hot staging adapter is gone. In its place is a sleeker, more integrated ring. No separation plate, no shielding grid, just a direct engine-to-engine interface. Clean, compact, and mechanically elegant. Could it be that SpaceX is moving toward a cleaner stage separation method? Without hot staging, how would ignition timing be handled? How is engine backflow prevented during separation? This is a milestone I've personally been waiting to see. The moment SpaceX ditches a workaround and commits to streamlined precision. It's the kind of refinement that signals a maturing vehicle, optimized for reuse, not just reliability. The adapter served its purpose in earlier flights, allowing upper stage engines to ignite while the booster was still attached, creating a brief overlap for thrust continuity. But it came at a cost: added heat shielding, structural complexity, and wear on the components. Its purpose now completed, it seems. Now, a quick update on the reasoning behind the removal. Engineering teams noted that hot staging introduced thermal stress on the Raptor nozzles and created uneven shock loads during separation. These factors not only reduced component life, but also complicated inspection and refurbishment after flight. With improved ignition sequencing and better tank pressurization timing, the new design allows for what's known as cold separation. The stages decouple first, followed by a brief pause, and then ignition of the upper stage engines in freefall. Static fire data from recent ground tests shows no major loss in performance. Engine response remains stable, and new sensors monitor thrust overlap timing with microsecond precision. And just in case, fail-safes are built in. If ignition drift is detected, fallback procedures automatically trigger to avoid engine interference. With all safeguards tested and new parameters validated, everything will be fine. Now, removing hardware is one thing, adding humans is another. So how exactly will Starship Block 2 carry people to Mars? Human transport capability. How will Starship Block 2 carry people to Mars? How is everything coming along at the crew configuration mock-up site? Over near the high bay, a full-scale passenger cabin prototype is being assembled. Robotic arms are carefully attaching glossy white panels to the steel framework, while engineers inspect pressure seals and mounting points. An oval-shaped hatch, noticeably wider than standard, has just been test-fitted. It's expected to serve as the main entry point for future crew. But this isn't just about checking tolerances. It's also about evaluating what boarding a spaceship will feel like for real astronauts. Farther across the site, you can spot a layout mock-up of sleeping quarters and a communal area. Yes, SpaceX is literally building a piece of Mars in the heart of Texas. From the pace of construction to the level of refinement, one thing's clear: they sure don't mess around. We have a fun update on the human-rated systems inside Block 2. The oxygen recycling module is now being integrated with a compact CO2 scrubber, both tucked neatly into the cabin wall to save space and improve accessibility. Crew seats are getting a full redesign: deeper recline, impact dampening, and most importantly, modular attachment points so the layout can change based on mission type. A lighting prototype has also been tested, simulating Martian daylight cycles. It's more than just aesthetics. The goal is to help passengers maintain their circadian rhythm and feel grounded, even while drifting through deep space. Every system inside the cabin is being built with human experience in mind. This isn't just a pressurized tin can. It's a spacecraft you can live in, not just survive in. And it's not just the systems, it's the schedule. With the current pace and successful test results so far, the timeline for integrating the crew module into Block 2 remains on target. Now the question everyone's asking: when exactly will we see Block 2 fly? When will Block 2 fly? Timeline, milestones, and realistic predictions. The news of the week is really all around the preparations for Block 2's first flight. We've just seen booster B11 rolled out for thrust testing at Massey, while new Block 2 segments are appearing almost daily outside the Mega Bay. It's as if the production pipeline is breathing in steel, welds, and rapid iteration. The assembly crew is prepping the next stacking stage. Temporary alignment fixtures are now secured by crane, and specialized insulation for the avionics section has been spotted arriving on flatbed trucks. A member of the launch tracking community at Launch Surfer captured drone footage of a full aerial sweep around the launch table. The signs are clear. We could be only weeks away from the first static fire. With all these developments, the big question is echoing louder than ever. When will Block 2 actually fly? A new stacking record, which is pretty cool. In just 48 hours, SpaceX completed 3 major segment joins for Block 2, marking the fastest assembly to date. Meanwhile, Ship 30 has passed its full cryogenic testing series, and Booster 10 was rolled back from the pad to make room for B11's thrust puck validation rig. That's a critical step before any integrated static fire can happen. According to the current schedule, and assuming no major delays from FAA licensing, a test flight before the end of this quarter seems genuinely plausible. And just to spice things up, one of the Boca Chica tracking cameras caught a satellite TV uplink test, which some speculate is an early dry run for live coverage of the upcoming launch event. So much movement, so many systems converging, and yet it's still just the beginning. It's kind of mind-blowing to think. Another 4 major milestones cleared just this week. And if you look at the pace in materials, data, and determination, one thing is clear. There's a lot more to come, but what does it all mean in the grander picture? Let's step back and look at what Block 2 is really setting us up for. We have big news on SpaceX's regulatory progress. Multiple test permits were just approved by the FCC and FAA in recent weeks. That means a Block 2 flight within this year is now a real possibility. A huge shift from the months-long wait times we used to see. This acceleration isn't just about paperwork. It shows how fast the space industry is moving. The progress here is just insane. The FAA is also testing a modular certification model, letting proven Block 1 systems carry over to Block 2. It saves time, though some experts question long-term reliability. And then there's the elephant in the room: NASA's future. If Block 2 lives up to the hype, government programs like SLS or Gateway could face funding pressure. Because the real question now isn't just who flies first, it's who stays funded. And that future is not currently looking bright.